Так. Так, я не понимаю, что происходит. Так. Так. Так, у меня почему-то что-то оказалось включенным. Я абсолютно не понимаю, почему. I'm sorry for these strange things. Nevertheless, so shall we start? I don't understand you. Okay, so I'm here. Okay, so now I don't see. Do you see? Oops, where is it? Oh, yeah. So this is this is our website. Have you seen it? Oop. It's so big, sorry. Wait a minute. I shall, oops. Do you see the address of our website?
Yes, we do.
Oh, okay. So we shall start, and I want to start from some ask. Should I be honest or not? So should I prove convergence of Eisenstein series? I give only draft previous time, and this is important. I think it's reasonable, huh? Yeah. So why? So I want to claim that this series is absolutely convergent. So for this, I consider the parallelogram around 0. Here is written pi 0. So it's parallelogram around the around 0 with of the same shape as original one generated by 1 and omega 1 and omega 2. And I want to, oops, no, it's not. Oops. Yeah, oops. So let me try to, no, where? Oh, yeah. I will draw a picture. So this is my lattice. I take such a parallelogram and fix also two disks. one which is in it, and another which contain it. So this will be R, and this will be rho. Now I split sum to the I split all elements of this lattice in two shapes. Short. So short means, wait a minute. Short means that its length is less than rho. Oh, no. Short means that its length is less than R, and long if they are bigger. Then for long elements of lattice, we have rather evident bound that, so if L is bigger than this number, then by triangle identity, we estimate the values of Z, of absolute value of Z on this parallelogram around. And so we get, from this bound, we get bound of the of this absolute value as some integral, and for sum over sum so partial sum will be bounded by corresponding sum of integrals. And I want to draw a picture. So what we have here, that I take integral of some parallelogram outside. The union of them lies outside of the disk of radius r, rho. So the integral can be bounded by integral over absolute value Z greater than rho. I integrate over domain which is inside this domain. And let me show here. Yes. So the result is that, oops, wait. Yeah, what it is here, that this sum is bounded, this convergent integral. The sum over short vectors, this is just a finite sum, so it's some finite number. So I see that any partial sum of this series is have upper bound. So this series converges as a sum of the positive numbers. Okay, so that's all. I have proved that the series is absolutely converges. Okay, do you have a question? No means no. Okay. So I want to pass now to the construction of periodic function, just one periodic function, according to Eisenstein, as it's somehow it's example of automorphic form, but it's really very important for me. I will use it. So I start from very, sorry?
I have a question.
Yes.
What is an automorphic form? We defined in the last lecture the notion of automorphic function. And
No,
what
automorphic form also, sorry.
the word form make some
Means
sense.
that this is not not invariant with respect to dilatation, but it's homogeneous.
No connections with the notion of differential forms.
No, it's actually different type of forms. Sorry. Yeah.
And
It's
linear
slightly
forms.
misleading. Sorry. Okay.
And linear forms, no connections.
No connection.
Okay.
Okay. So so I want to construct periodic function. For this, I can use the following idea that so we have space of functions, and we have action of group Z on it by shifts. Then periodic function means that it is invariant with respect to this translation. Do you agree? Okay. So I want to construct. So I have action group of a group on a vector space, and want to construct an invariant element. There is a universal way. Just average the action on some vector by all elements of group. Sum of G over G. G of V is invariant.
I'm sorry. Our group is finite or discrete?
I don't. Okay.
Or maybe compact.
I get general fact. Okay, it's a very good question. So if I want to take a sum, this means of course that I think that the group is discrete. For finite group, it's okay, yeah? But what happens for infinite group? For infinite group, you have infinite sum. So you shall explain what is meaning of it. So let me try to explain what happens in our case. So we have the vector space of the functions on the real line. We have action by shift group, and want to average. So the simplest case is if I pick a monomial. The simplest function is of course monomial for me, and so if I some misprint, sorry. So if I want to average positive powers of x, then we have absolutely no chance to simply define what is its sum. This series is divergent just because the terms don't tend to zero. The terms of sum doesn't tend to zero. But for negative powers, the situation is different, and so if the exponent is less or equal than -2, then this sum is divergent. I will prove it in a few minutes. More interesting case is that when k is equal to -1. Okay?
Excuse me, is our vector space one-dimensional?
No, of course. This is the space of all function on real line.
Okay. So we have a real line as a vector space. Okay, great.
No, not real line. Function on real line is my vector space.
Okay, I got it. Thank you.
Yes.
And in which point the sum diverges? You say
What?
The sum diverges when k less than -1.
Why?
Or in
No. when power is less than -1, when the exponent is less than -1, then we have the following sum. So what is this sum? It's okay, it isn't written here, sorry. I write only, okay. So wait a minute, sorry. So I want to define what is for any function, some function f of x minus mu, sum from mu equal to minus infinity to infinity. Is this series convergent or not? Okay, let me show you that if f of x is x in power m, if m is positive, then this series evidently very divergent, right? So f of x minus mu tends to infinity and not to 0. So it's sum of the series in which terms growth. Now, so if m is less or equal, then strictly, okay, -2, then what we have? So we have the following bound. So x minus m absolute value in power m is less than, okay. So let me fix, I want to prove convergence on any bounded set. So let x, absolute value of x is smaller than some number k, some integer. Then, so what is x minus m is bounded by k plus m. Sorry. Again, oops, where is it? Oh. Sorry, it's okay. So, sorry. Evidently, x minus m for such x is bounded by k plus m. Oh, no, it's wrong, sorry. It's greater than k minus m, okay? So for negative powers, x minus m is less in power m, no, is less than mu minus k. So sum from k to infinity is bounded sorry. X minus 7 more m. As m is negative, it's bounded by sum of mu minus k from k to infinity in power m, and this is convergent. Okay.
Yes,
So
thanks.
this
Yeah, I don't.
series for very negative M is absolutely convergent. But for k equal to -1, so we have bound like mu in power -1, and this series is divergent. But here Eisenstein introduced some beautiful trick, so that instead of taking separately limit to plus infinity and minus infinity, his assumption is that let me take sum from -m to m, and simultaneously both goes to 0. Then it is again convergent, as negative cancel positive somehow. So here is all written. So we again have such a bound by m mu square. So this series is convergent. Unfortunately, if I redefine this sum in such way, then periodicity is not so clear. It should be proved, as this way of summation breaks translation invariance. But nevertheless, we can prove. So this is a way to regularize this sum. And now, so formal definition. Epsilon n is such a sum in power -n for n greater than 1, and epsilon 1 is this regularized in the sense of Eisenstein's sum. Now, so you see what I want to claim. Okay. So what is the proof? So the main idea of the proof, and here is written this convergency property, that so I prove that this series for positive n greater than 1, this function, this series is absolutely convergent. Here all bounds are written. So from this we immediately conclude periodicity. Indeed, it's just the fact that absolute convergent sum does not change, series doesn't change if I change order of summation. I think it's Riemann theorem, yes? Okay. Now, parity property, that it's even or odd, is absolutely evident, just again, resummation. So for formula of derivative, essentially I again use absolute convergency, but not of epsilon n, not epsilon n plus 1. So it's condition when I can differentiate functional series term by term. It's standard fact from calculus. I will not discuss it. It will be your homework. Okay. And now, so which is not absolutely trivial, it's invariance of epsilon 1. So well, so again, it is written here that the defect in such a sums. Yeah. So I also don't understand what shall I explain here more. Okay. So I construct a bunch of functions which are periodic. Now I want to study them a little. First, I define the number gamma m. So for somebody who about values of Riemann zeta function, gamma of odd is 0, and gamma of even is doubled zeta value at this point. And this series converges again by the same integral. Well, no, it's also classical. Shall I explain why it converges? I hope no. Then at rather big neighborhood of point 0, we can represent epsilon 1 in such a way. Proof. Okay, so proof. First of all, what is the
X
origin
and
of this
M.
sum? Sorry?
X and mu is the same variable, or no?
What?
Put gamma m equals sum. On the right we have mu, and on the left
What
we
is
don't.
sum over mu? Gamma m is sum over mu, non-equal to 0 of negative powers of mu.
Mu is integer number.
Mu is integer, yeah. Oh, sorry, it's not written.
Okay. Okay.
Yes. So, what is the origin of this formula? The origin of this formula is just geometric series. I expand 1 over 1 minus s into geometric series and substitute it to this sum. Well, all is written here, with one exception that we shall check. So here where is trouble is that we shall, for getting this formula, we shall replace summation by mu and by m. And so for this, well, my way to prove it, of course, there is a lot of way to, oops, sorry, again misprint. So I get stupid bound, from which I see that I can bound all this sum by product of two convergent. So I have succeeded that this series is absolutely convergent. And this is also your homework for person who want. Okay. So the crucial part of this story is addition formula. That we have some nonlinear relation between these periodic functions. And the basic for this is very important formula in mathematics, which is that P plus Q is equal to P plus Q. Do you agree that this is true? This is written on the third line. And so if I divide it by product of all three terms, I get the fourth formula in this bunch of formulas. Sometimes this formula is called by Arnaud relation. And well, of course, it's known to Einstein, which was very earlier than Arnaud. But nevertheless, we have such a formula. There is a lot of interpretation. It's expansion into well, so it's important in calculus for integration. Nevertheless, it's evidently true. Now I can sum it over m. in Eisenstein's sense. This is okay. On the right-hand side, I get such expressions. I can sum. At the left-hand side, I am not able to sum, as here we have mu in both denominators. Again, in the right-hand side, I use periodicity of epsilon1, which I have proved. At left, I get nothing. After this, I sum over nu and get in right-hand side beautiful expression epsilon of x plus y plus x times epsilon1 of x plus epsilon of y. So if we have here before identity, then we have, here's misprint, it's y. We have a addition formula that epsilon1 of xy can be expressed in terms of epsilon1 of x and epsilon1 of y. Sorry. Yeah. But unfortunately, in order to get this product, I shall, in this sum, change order of summation. And this is just wrong. So I want to say you that epsilon essentially is cotangent. Cotangents. And addition formula for cotangents is not so simple. So the problem is that this series is convergent not so good. We can try to solve this problem by writing this beautiful formula. This is just differentiation by x and y of the original one, of this one, of first here. But now, if I try to work with this formula, then it works, because this series converges absolutely, and I can change order of summation, but I get much worse formula. There is a lot of beautiful another formulas, and in the book of length, some of them are written. But I want to deduce something which is important for me. So for this, I use the expansion of my function near zero. Yes, so we, if we average this formula, then we get such a formula, which is not so nice, but it is. Okay, so now I substitute in this formula expansion of near y equal to 0. So if y is near to 0, then epsilon 2 of x is epsilon 2 of x, and epsilon 2 of y is y over 1 over y square plus gamma 2. Yeah, so all is written here, yeah? And now I want to compare term by term and get some quadratic relation on epsilons. I don't. All this is written in the book of Whale. So another expression is if I take expansion near x plus y equals 0, and after some tricky combination, I deduce the differential equation for epsilon 1. Again, here, of course, I use the d epsilon 1 over dx is epsilon 2 and so on. This is differential equation to cotangents. But I don't want to go in this direction, as I want to pretend that I'm absolutely stupid person, that I don't know what is trigonometric function and I don't know what is exponential function. So instead of this, so I just define pi tilde as square root of 3 gamma 2. Maybe some of you know that values of zeta function at 2 is equal pi square over 6. Gamma 2 is 2 zetas, so 3 gamma 2 is really pi square, but somehow I deduce it absolutely independently. Then if I differentiate this formula, then I get that the derivative of e of x is 2 pi I e of x. Here's missed I, sorry. Second, just by definition, e of 0 is 1. As e1 tends to infinity when x tends to 0. Okay? But now I can calculate the Taylor series of this function at 0. And from these two properties, I get immediately series for exponential of 2 pi I, pi tilde I, x. So I get exponential function. So I prefer this way as I construct something periodic. So it's some global thing, global property. And after this, I deduce from it its local behavior near with 0. So formal, so just for power series. It's very hard to deduce from power series global behavior. So global things are more complicated than local. So here's written a lot in this text is in this part is hidden a lot of classical facts. So for example, Euler formula, which relates exponential and trigonometric function. Here somehow is hidden the formula for infinite product for sine function. Yes, so it's I strongly recommend you to think about to check all this story in the book of Whale. So oops. Okay, so we have finished what I want to explain, but we have a lot of time. So then, what is reasonable to do? No, I really don't see. Okay, so maybe.
Question.
Huh?
What do you mean by cotangents? You
Cotangent for cos over sine, cosine over sine.
Okay.
But this is cosine over sine of half of angle. Okay, maybe it's really yeah. I demonstrate you something. What is okay? Maybe yeah. It's reasonable to explain what really happens. So what really happens is that epsilon 1 is pi Oops, sorry. Cotan of pi x. Okay. Cotangent is pi periodic, not one period, not 2 pi periodic. Okay. So by Euler formula, so this is what? This is pi cosine of pi divided by sine of pi x. And by Euler formula, it's exp of pi I x over 2 plus 2 pi I x over 2. And here
Без
minus.
деления надо нафиг вроде.
So cotangent of half of angle and exponential are related by fractional linear transformation, which I inverse in my talk, and so deduce exponential function from cotangent.
Okay.
Okay. Huh?
Okay. I didn't
So maybe
get.
So maybe it's reasonable also. Wait a minute. No. So then discuss. It is not so close to automorphic form, but rather close. Let me look at this beautiful formula. The d epsilon 1 of x over dx is equal to minus epsilon 1 of x square minus 3 gamma 2. Yeah? So let me show you what is sequence of it. First, I think that somebody here knows it. So I want to write some epsilon 2 of x is equal to epsilon 1 of x square minus 2 gamma 2, right? Is it, wait, sorry. Oops. Yes, minus 3 gamma 2. Now let me substitute to it the expansion near x equals 0. So what I have here, 1 over x square minus gamma 2 x minus gamma 4 x cubed and so on is equal to, let me put it, 1 minus x, 1 plus x, plus. It's something strange. Wait, here should be plus 2 gamma. It's misprint.
And there should be also even powers of x in the expansion. There should be also even powers of x in the expansion.
Oh, yeah. Sorry, thank you. this is constant term, and this is, oops, square. So what we have, 1 minus x minus gamma 2x square. So I write only first terms. First is, of course, 1 over x square, it's okay, plus minus 2 gamma 2x. And the next will be, oh, sorry, no, this is wrong. Yes, I shall put 3. Gamma 2 of x, and here I shall put minus gamma 4 x cubed. So what I get here, plus gamma 2 square, wait a minute, yeah, plus 2 sigma 4 x cubed, and here it's also x cubed, x square. Oh, sorry. Minus 2 minus gamma 2x, 2 gamma 2x, plus gamma 2 square x square, minus 2 gamma 4 x square, plus and so on, plus 2 gamma 2. So we have cancellation of first terms, 2. But after this, I get nonlinear relation, which relates gamma 4 and gamma 2 square. You see? Gamma 4 should be equal to gamma 2 square. It's very absolutely unclear a priori fact that values of zeta function are subject of linear quadratic relations. And such a trick uses a lot of times in this theory of modular forms. So we have some generalization of it, but unfortunately in full generality, I don't know what is analog of this statement. Okay, so I want to mention also that something strange happens here. You see, so we have function epsilon 1 whose expansion at 0 contains numbers gammas, which are more or less values of zeta function, so sum of negative powers. At the other end, Fourier expansion, the expansion of exponential, we also know it's just a tail expansion which comes from the differential. And so if we compare these, we get expression of the values of zeta function at positive even. In terms of Bernoulli numbers, it's just substitute, calculate in opposite directions, and it's really a very simple thing. So it's also some So you see that somehow it's what I use here. I use almost nothing. I use for deducing this equation. I use expansion of epsilon at 0, but after this I reconstruct this expansion in absolutely different terms. Okay, so now maybe it's a good time for discuss how many persons from here want to wait a minute, sorry. Wait a minute, where is it? Sorry. Yeah. So I have some list of, sorry, yeah, of list who will pass through test. Wait a minute. How much person here want to pass through exam? I have two.
I'm not on the list, but I'd like
Eugenia,
to.
You want to pass? Okay, and so, oops, because, oh, yeah. So this is, so this is my list. Have you seen him?
Yes.
Okay. Is somebody else who wants to pass through examination? So, Eugenia, you, yeah?
Mhm.
Okay. So we'll change your individual pay plan, yeah? Okay. So because I have not so much time for discussing homework. You see, it's a rather hard job. So I prefer to talk about homework only for person for whom it's important by administrative reasons. Okay?
So is the homework oral or written?
I think that this will be that you shall write something, and after this I discuss what is written by Zoom, because so somehow so the sense is that I will be sure that you understand what is written. It's not new problems, you see.
Mm-hmm.
Okay. So again, the exercise will be rather elementary, but this elementary introduction, so this is okay. Okay. Wait a minute. So a few minutes. Okay, I have information that the presentation is on this side. Let me check. Oops. No, sorry, maybe I sent you. Oh, no. Oh, yeah. Yeah, here is it. Okay, very good. So I think that it's enough for today. And in few days, so homework appears on this site. Sorry, but maybe okay. Nevertheless, there is our page home. So okay, and I think that I will give you 2 weeks for preparation of this homework. Is it okay? Or it's so well. Sometimes students explain that if they have so much time, then they aren't able to do it. So I will ask you. Okay. So if I think it's okay.
Sorry.
Maybe yeah. Maybe I will
Sorry.
explain you also something.
Sorry.
Just in order to prepare to the next lecture. Okay. So as I have explained you, we in the theory of automorphic form, we use the following fact that upper half plane is quotient of group SL2R by SO2. Okay, and so somehow this corresponds to the fact that H parameterize lattices with generators. Indeed, what is SL2R? SL2R, this is set of bases of C as R vector space. Sorry, this is wrong. This is wrong. It's oops. JL2R. Okay. Do you agree? Any basis omega 1, omega 2 can be constructed as A, B, C, D of the basis 1I. Okay. Now, but I want to think about not about lattices, but about lattices modular dilatations, modular complex dilatation. So it's modular C star. So we have the following picture: GL2R. Here we have C star. Here we have SL2R, and its intersection is just SO2. This is more or less standard isomorphism in small dimension. So this show me how to realize. Okay, now the automorphic functions are SL2Z invariant functions on H. How to realize automorphic forms? So if I combine all of this in one group, it's functions on H, which are SL to Z and SO2 invariant. You agree? I say nothing. So now the funny thing is that so automorphic form is not invariant with respect to SL2Z, but is invariant with respect to SO2. The beautiful fact is that if I take the following function on the group, but now I multiply it also by Ci plus D in power K. Then it becomes invariant, and this is automorphic form of weight K. Maybe here is plus minus, I forget exactly. It's evidence check. So then this function is SL2Z invariant, but under action S of SO2, it transforms by character, by Kth character of SO2. Okay? Let me check. For this, I shall check property of this expression, C2 plus D, when I act on A, B, C, D, either from left or from right. And this is simple calculation which shows that, so we can calculate its its property. But if so, if my calculation is correct, then you see that automorphic form is related with so-called induced representation or co-induced, I forget. What is either induced or co-induced representation of SL2R, and it is induced or co-induced from the complex subgroup SO. This is also the standard part of the this triple I have, as I have explained. Okay, so I think that we shall stop. Thank you, and have a nice day. I try to put all on the site rather quickly. Goodbye.
Can I ask you a question?
Yeah, sure.
Until what day we should pass our homework?
Sorry, again?
Until what day we should pass our homework?
I think it's approximately 2 weeks you
Okay.
have for
Thank you.
preparation. Sorry. Давайте по-русски.
Я поняла, спасибо большое.
Ага, хорошо. Okay. Have a nice day.
So you mean we should prepare our homework?
To which day? Sorry. You have for preparation homework, you have approximately 2 weeks after I put it on the website.
Sorry, you mean we should talk about our solution in our lecture, but not submit it to your email?
No, you should. Okay, I put, sorry. I put it on the website. Okay, sorry. It's a good idea. Sorry. Okay. So that's all. Goodbye.